Okay, Assalamualaikum warahmatullahi taala wabarakatuh and a very good morning to everyone. So, in this video, I will continue my lesson on fluid mechanics DMM 2533 for our next chapter and that falls under CO2 cause outcome 2, which is fluid friction, chapter 5. Okay, so in fluid friction chapter, we will learn about some introduction and basic uh, knowledge or background on flows, and then we will learn about laminar and turbulent flows in more details, including the calculation of the Reynolds number. And then we will look at the entrance region and entry lengths. What are these? And then we will study in detail about laminar flow in pipes, how to calculate pressure drop and head loss, and then we also will study in detail about turbulent flows in pipes, where we will calculate the turbulent shear stress and how to determine the turbulent velocity profile. And then last, we will see on the Moody chart and the Colebrook equation. Okay, so to start on the introduction and basic concepts of internal flow. So what is internal flow? Liquid or gas flow through pipes or ducts is commonly used in heating or cooling applications and fluid distribution networks. This fluid is forced to flow by a fan or pump through a flow section. This fluid is forced to flow by a fan or pump through a flow section, and then we have this parameter friction, okay, which directly related to the pressure drop and head loss during flow through pipes and ducts. Pressure drop is important to determine the pumping power requirement. So that's why piping system involves pipes of different diameter connected to each other by various fitting to route the fluid, valves to control the flow rate, and pump to pressurize the fluid. So in this chapter, we will learn more. It's not chapter but the subtopic after this. We will learn basic knowledge about flows. What are flows in pipes or flows in ducts? Okay. So internal flows through pipes, elbows, teeth, valves, etc., as in this oil refinery, are found in nearly every industry. Alright. So flow section. Okay, flow sections are actually divided into pipes and also ducts. Okay, so what is pipes and what is ducts? For pipes, is where the flow sections of circular cross section, especially when the fluid is liquid. Okay, we call it as pipe. However, for small diameter pipes, we call it as tubes, as shown in this figure. Circular pipe, water 50 at ATM. And then for ducts, flow sections of non-circular cross sections, especially when the fluid is gas. For example, showing here rectangular duct air 1.2 atm. You see the flow also different. One is fluid and another one is gas. Okay, so that's the difference between flow sections of pipes and ducts. Alright, so most fluids, especially liquids, are transported in circular pipes. Why? Because it can withstand large pressure difference between the inside and the outside without undergoing significant distortion. So sometimes in exam, they will ask you what are the benefit of fluid that transported in circular pipes compared to ducts. Okay. Alright, so for tubes, usually used in applications such as heating or cooling system of buildings where the pressure difference is relatively small, the manufacturing and installation costs are lower. So that's the benefits of flow section using tubes. Alright, so now let's see a flow within a pipe. Okay, so here we have, for example, a circular pipe. Okay, and the velocity of the fluid transport within this pipe with velocity average. Okay, so fluid velocity in a pipe equal to changes from, okay, so we have velocity profile here. So this velocity profile, it changes from zero, okay, from zero at the wall. This is wall, okay, the pipe wall. So the changes, fluid velocity in the pipe changes from zero at the wall because of the nose deep condition to a maximum at the center of the pipe. Okay, average velocity VAVG is actually the average speed through a cross section. So you cut through this section, and the V average is the average velocity for this cross section. Okay, VAVG remains constant in incompressible flow when the cross-sectional area of the pipe is constant. Alright, so VAVG may change in heating or cooling application due to changes in density with temperature. Okay, it's of course like that. Okay, V average at some streamwise cross-section can be determined from the conservation of mass principle requirement as shown in this equation. Okay, m dot equal to density times width V average times width area at the center of the pipe. Alright, so here I show you some figure of laminar and turbulent flow. So from here we can roughly see that the upper figure is laminar, and then the below figures are turbulent. Okay, okay. Similar with this one. Okay, this is laminar. Okay, the flow is much more steady compared to turbulent. Okay, it is much more chaotic. Alright, so laminar and turbulent flows. So we have flow of a smoke here. I'm not sure, maybe it's smoke or uh, some fluid. Okay, so here we have a laminar flow. Okay, laminar flow which is much more steady, and then we have turbulent flow which is much more chaotic. Okay, similar with this one. Okay, smoke flow from a candle. Okay, we have laminar flow here and turbulent flow here. Alright, so we have at the in the between of laminar and turbulent flow is called transitional flow. Okay, what is transitional flow? It occurs over some region in which the flow fluctuates between laminar and turbulent flows before it becomes fully turbulent. So we have laminar, and then it will transition, and which called as transitional flow, and then it will become turbulent flow, fully turbulent. Okay, in turbulent flow, velocity fluctuations and highly disordered motion. In laminar flow, it is much more smooth, streamlines, and highly ordered motion. Okay, now I believe that you guys already roughly understand the difference between laminar, transitional, and also turbulent flow. Alright, regarding Reynolds number, okay, the transition from laminar to turbulent flow depends on A, geometry, B, surface roughness, C, flow velocity, D, surface temperature, and also E, type of fluid. Okay, actually we can calculate the Reynolds number using this equation. Reynolds number equal to inertial forces divided by viscous forces, and you will get this equation. Alright, so Osborne-Reynolds denotes that flow regime depends mainly on the ratio of inertial forces to viscous forces in the fluid, which now we call it as Reynolds number. Reynolds number is expressed for internal flow in a circular pipe, okay, rho V average times D over mu. Okay, what is mu? Mu is the kinematic viscosity of the fluid. Okay, meter squared over second. Reynolds number is a dimensionless quantity. So kinematic viscosity equal to viscous diffusivity or diffusivity for momentum. So we have Reynolds number, and then from Reynolds number we can also calculate the kinematic viscosity using this equation. Okay, mu over rho. Okay, so mu here is dynamic viscosity, and mu here is kinematic viscosity of the fluid. So it's two different things, dynamic and kinematic viscosity. Alright. So I actually already explained before the difference between laminar and transitional and also turbulent flow, and this actually depends on its Reynolds number. So for laminar flow, the Reynolds number must equal or below than 2300. Okay, for transitional flow, it is between 2300 to 4000, and then for turbulent, it must be equal or larger than 4000 Reynolds number. So now, a little bit of quiz. Two questions. The inertial forces are large relative to the viscous forces. Thus, the viscous forces cannot prevent the random and rapid fluctuation of the fluid. Okay. A, large Reynolds number, flow is turbulent. B, small Reynolds number, flow is turbulent. C, large Reynolds number, flow is laminar. D, small Reynolds number, flow is laminar. So which one? Okay, so of course, large Reynolds number, flow is turbulent. Okay, you can see here. Alright, the viscous forces are large enough to suppress fluctuations and keep the fluid in line. Okay, which one is the answer? Large Reynolds number flow is turbulent. Small Reynolds number flow is turbulent. Large Reynolds number flow is laminar. Small Reynolds number flow is laminar. Okay, of course D. Small Reynolds number flow is laminar. Okay, so this is the answer for this one. Viscous force are large enough to suppress fluctuation because we have viscous force here, and then and it can keep the fluid in line. So of course we will get smaller Reynolds number, and then we will determine it as a laminar flow. Alright. So Reynolds number at which the flow becomes turbulent is called the critical Reynolds number, RE critical. RE critical is different for different geometries and flow conditions. For internal flow in circular pipe, the critical Reynolds number is equal to 2300, and the internal flow in non-circular pipe, Reynolds critical is based on the hydraulic diameter. So for non-circular pipe, we have to calculate the Reynolds number based on the hydraulic diameter. So for example, you have a wind tunnel, and of course wind tunnel we don't use circular pipe or circular shape. We usually use a square duct or a rectangular duct. Then you have to calculate the hydraulic diameter first in order to get the D hydraulic. Okay, and then using D hydraulic, you can substitute into this equation Reynolds number. Okay, into this equation. Okay, this equation DH. Okay, just now we already learned about some introduction and basic background of the internal flow, and then we learn a little bit about laminar and turbulent flows, and also the equation of the Reynolds number. So I will continue on the entrance region and also the entry lengths, and then I will follow with a detailed discussion on laminar flow in pipes. Okay, we will see the equation to calculate pressure drop and head loss. Alright, so entrance region. Okay, what is entrance region? We have a flow, okay, in a pipe like this. So here is the inlet, and the right hand side is the outlet. Okay, we can see that the flow is developing, okay, is flowing inside the pipe. Okay, first the V average, if we cut the dimensional here, we will have an average velocity. Okay, V average same at this point, okay, at the inlet, and then the velocity is actually developing, okay, and the velocity profile as well. Okay, and until it reach until it reach to the maximum point at the center of the pipe. Okay, whenever the velocity reach the maximum point at the center of the pipe, we can call it as fully developed velocity profile. Okay, means the velocity profile cannot be developed anymore, since it is fully developed at this point. Okay, so from the entrance to the developing velocity profile, fully developing velocity profile, we call it as hydrodynamic entrance region. And then for after the fully developed velocity profile, we call it as hydrodynamically fully developed region. Okay. Um, So this figure shows the velocity gradient develops along the pipe. So it actually is the same. If we see this wall as a surface, so the boundary layer is developing from windward, means inlet, to downward, okay, means to the further in the pipe. Okay. So due to no-slip condition, the fluid particles in the layer that in contact with pipe wall come to a complete stop. Okay, it's at this point. Okay, you already understand. And then this causes the fluid particles in the adjacent layers to gradually slow down due to friction. Okay, or drag. Okay, the velocity of the fluid at the pipe center has to increase to keep the mass flow rate through the pipe constant. So that's why you will obtain a maximum velocity value at the center of the pipe, okay, at this fully developed region. Okay, all right. For velocity boundary layer, the region of the flow in which the effects of the viscous shearing forces caused by fluid viscosity can be divided into two regions. We have boundary layer region and irrotational core flow region. Okay, this is in irrotational core flow region. Okay, what is boundary layer region? The viscous effects and the velocity changes are significant. Okay, and for irrotational core flow region, the frictional effects are negligible, and the velocity remains essentially constant in the radial direction. That's why we have this V average here. Okay, the boundary layer thickness increases in the flow direction until the boundary layer reaches the pipe center, means fully developed velocity. The region from the pipe inlet to the point at which the velocity is fully developed is called hydrodynamic entrance region. Length of this region is called hydrodynamic entry length. The region beyond the entrance region where velocity profile is fully developed and remains unchanged is called hydrodynamically fully developed region. We already discussed this in a previous slide. So now you understand how how fluid flows in a pipe. Okay, and how the viscous and the friction effects the velocity profile in the pipe. Alright, so now hydrodynamically fully developed region. So this is hydrodynamically fully developed region, means at this point, okay, at this point, okay. So the boundary layer is fully developed. In the fully developed flow region, the velocity profile does not change downstream, means you will always get this profile until downstream because it is fully developed. It cannot be developed again. Thus, the wall shear remains constant as well. Okay, that's why the wall shear also remains constant because it is already fully developed. Alright, so the wall shear stress tau W is the highest at the pipe inlet. Boundary layer thickness is the smallest. Okay, you can see here for this graph, this is X, means streamwise. Okay, inlet to the outlet, the shear stress is the highest at the inlet. How about the boundary layer thickness? Okay, boundary layer thickness is the smallest. Okay, at the inlet. The wall shear stress decreases gradually to the fully developed region. Okay, so here in entrance region, it gradually decreases until it reach the fully developed region. Okay, the pressure drop is higher in the entrance regions of a pipe. Effect of entrance regions is always to increase the average friction factor for the entire pipe. This effect is significant for short pipes but negligible for long pipes. Okay, I believe you already understand this for the entrance region background, basic knowledge of the entrance region. Alright, the hydrodynamic entry length is usually taken to be the distance from the pipe entrance to where the wall shear stress reaches within about 2% of the fully developed value. So for non-dimensional hydrodynamic entry length for laminar flow can be calculated using this equation. Okay, entry length lamina over D equal to 0.05 Reynolds number. For non-dimensional hydrodynamic entry length for turbulent flow can be calculated using this equation. And for approximation of hydrodynamic entry length for turbulent flow is almost around 10. Okay, so this is for entry length. Alright, now let's discuss a little bit about laminar flow in pipes. Okay, flow in pipes is laminar for Reynolds number similar or lower than 2300. The flow is fully developed if the pipe is sufficiently long relative to the entry length so that the entrance effects are negligible. Velocity profile for laminar flow can be obtained using this equation. Okay, we actually can uh, do the velocity profile using this equation if you know the velocity average. Okay, and then these are two parameters. Okay, the maximum velocity occurs at the center line and is determined by above equation by substituting r equal to 0. Okay, therefore, the average velocity in fully developed laminar pipe flow is one half of the maximum velocity. Okay, so the average velocity for laminar flow is actually one half of the Umax in the pipe. Okay, and please take note that the flow is fully developed if the pipe is sufficiently long. However, these entrance effects are negligible if it's short pipe. Okay. So now, for pressure drop and head loss, pressure drop is a quantity of interest in the analysis of pipe flow since it is directly related to the power requirement of fan or pump. Pressure drop for laminar flow, this equation represents the pressure loss, delta PL, when a fluid of viscosity mu flows through a pipe of constant diameter D and length L at average velocity V average. So you have this equation to calculate the pressure drop or pressure loss. Okay, sometimes in the question they will ask you to determine the pressure loss of the fluid in the pipe. Okay, so pressure drop for all types of fully developed internal flows, either laminar or turbulent flows, circular or non-circular pipes, smooth or rough surfaces, horizontal or inclined pipes can be determined using this equation. Okay, so this equation is all in Chungel textbook. You can read more in Chungel to get much more detailed information about pressure drop. Okay, so the head loss represents the additional height that the fluid needs to be raised by a pump in order to overcome the frictional losses in the pipe. Okay, we already learned in the previous slide that the internal flow needs pump to pump the fluid inside the pipe. So head loss is important. Is one parameter that is important to for us to know how much the height of the fluid that needs to be raised, okay, in order for the pump to overcome the frictional loss in the pipe. Okay, the head loss is caused by viscosity. It is directly related to the wall shear stress. Okay, and the equation is written like this: HL equal to delta PL over rho G. So what is PL? PL is the pressure loss. Just substitute into this equation. Above equation can be used for either laminar or turbulent flow depending on how the friction factor F is obtained. Okay. So for the friction factor, it's already written in this table. It is already given. So you can use this friction factor for fully developed laminar flow in pipes of various cross sections. The Reynolds number for flow in this pipe is based on the hydraulic diameter. AC is the cross sectional area of the pipe and P is the wetted perimeter. Okay. So now we finish explaining about laminar flow in pipes. Okay, let's continue on turbulent flow in pipes, where we will learn about turbulent shear stress and also turbulent velocity profile. Okay, for turbulent flow in pipes, most flows encountered in engineering practice are turbulent. Okay, turbulent flow is a complex mechanism dominated by fluctuations, and despite tremendous amounts of work by researchers, turbulent flow is still not fully understood. That's why we have one equation involving this turbulent flow, which called the Navier-Stokes equation. Okay, so until now we researchers still cannot solve this Navier-Stokes equation due to its complication. Okay, thus experimental and empirical are developed for various situations. So turbulent flow is characterized by disorderly and rapid fluctuations of swirling regions of fluid called eddies throughout the flow. So all of these swirling, okay, regions in this fluid is called eddies. Okay, these fluctuations provide an additional mechanism for momentum and energy transfer. So before turbulence, the fluid particle is like this, but then after turbulence, it becomes very chaotic. Okay. Alright, so in laminar flow, we already learned before, fluid particles flow in an orderly manner along path lines. Momentum and energy are transferred across streamlines by molecular diffusion. However, in turbulent flow, the swirling eddies transport mass, momentum and energy to other regions of flow much rapidly than molecular diffusion, greatly enhancing mass, momentum and heat transfer. Even when the average flow is steady, the eddy motion in turbulent flow causes significant fluctuations in the values of velocity, temperature, pressure, and even density in compressible flow case. Okay, what does it mean by significant fluctuations? Okay, you can see from this figure. Okay, this is an example of velocity u. Okay, we have u equal to u bar plus u prime. U bar is actually the average velocity of this fluid. Okay, from 0 to t. Okay, from time 0 to t, the fluid flow with average velocity u prime. And then since this fluid flow is turbulent, then there are lots of fluctuations happen. These fluctuations, as you can see in this figure, is actually u prime. Okay, so all of these fluctuations, height of this fluctuation is called u prime. Okay, so u is represent with the average velocity plus with the fluctuation velocity. Okay, figure shows the variation of the instantaneous velocity component u with time at specified location, which can be measured by hot wire anemometer probe. Okay, velocity can be expressed as the sum of an average value and fluctuating component. This applies to other properties too, such as velocity component in y direction, v equal to v bar plus v prime, pressure P equal to P bar plus P prime, and temperature T equal to T bar plus T prime. So depends on which properties you are looking for, but for turbulent, it is represented with two components, okay? The average and also the fluctuating component. Alright. So instantaneous turbulent shear stress. What is instantaneous turbulent shear stress? It is the shear force per unit area due to the eddy motion of fluid particles. So it is particularly on the turbulent flow. So the shear stress that for per unit area that happen due to the eddy motion is called the instantaneous turbulent shear stress. So the equation is written as here. Tau turbulence equal to minus negative rho density uh, times with u prime v prime average. Okay, this time average of the product of the fluctuating velocity components u prime and v prime. As you know, we have x direction velocity. It is u equal to u bar plus u prime, and we also have y direction of velocity v equal to v bar plus v prime. So this term is actually the product of the fluctuating velocity component of u prime and v prime. Alright, so this equation is called the instantaneous turbulent shear stress, or we also call it as Reynolds stress or turbulent stress. Okay, so the random eddy motion of group particles resembles the random motion of molecule in gas, colliding with each other after travelling a certain distance and exchanging momentum in process. Therefore, momentum transport by eddies in turbulent flows is called the molecular momentum diffusion. Okay, it is happening here. Okay, in laminar flow, it is called molecular diffusion. Okay, all right. So the previous equation just now, the Reynolds stress, okay, or instantaneous turbulent shear stress can also be written in terms of the eddy viscosity, okay, or turbulent viscosity, mu t, which equal to the momentum transport by turbulent eddies. So the viscosity of each eddy is actually equal to the momentum transport by turbulent eddies. So we can determine the momentum transport of a particular eddy at one particular time. Okay, and then we also can rewrite this equation in terms of kinematic eddy viscosity. So this one you can replace it with mu rho plus times with mu plus mu t. Okay, so this is kinematic eddy viscosity or kinematic turbulent viscosity. Okay, also called the eddy diffusivity of momentum. So if in the question they ask you about molecular momentum diffusion, then you know which one you're going to use. Okay, either you want to represent it with eddy viscosity or kinematic eddy viscosity. All right. So for turbulent velocity profile of turbulent flow, okay, turbulent flow, this is the laminar flow we learned before. So it is different, totally different with laminar flow. And in turbulent flow, we have several layers. Okay, first at very close to the surface, wall surface. Okay, this is wall surface, a pipe wall surface. We have viscous sublayer where the viscosity effects are dominant. Okay, because we have surface drag here. Okay, we have a surface. If the pipe inside here is a rough wall, so the viscous sublayer maybe little bit thick, and then we have buffer layer, and then we have overlap layer and turbulent layer. Okay, so to explain in detail what is viscous sublayer, it is a very thin layer next to the wall. The velocity profile in this layer is very nearly linear, and the flow is streamlined. Buffer layer, a layer where turbulent effects are become significant, but the flow is still dominated by viscous effects, like this one, okay? Like the first layer, okay? The third layer, inertial sublayer, a layer where turbulent effects are more significant, but still not dominant. And then the fourth layer, outer layer, the remaining layer in which turbulent effects dominate over molecular diffusion's viscous effects. So the turbulent layer or outer layer, the turbulent effects dominate over the viscous effects. Okay, so that's all for the turbulent velocity profile. Actually, we have finished chapter 4, and I will assign you an assignment for not exactly for this chapter, but then it comprises from chapter 1 to chapter 4. Okay, we have another one chapter, okay, which is chapter um, chapter 6 pump, okay, uh, uh, that falls under CO3, okay, that we are going to learn in the next video. Alright guys, thank you very much. Assalamualaikum warahmatullahi taala wabarakatuh.